Okay, so this is a word that I mentioned last time, but we didn't actually use very much, and it is determinant. So it's a special number that can be calculated from a square matrix, right? It's called the special number because in reality it has to do with the change of area, and that's a complex geometric representation that you can study in the class called linear algebra. And if you're going to continue on in like engineering or mathematics, you'll see it, and that's a cool connection. But right now we can just call it a special number and call it good. It's going to be denoted either as det of A, right, for determinant of A, or it almost looks like the absolute value signs, but it really means the determinant of that matrix. So we did this last time, but for a 2 by 2 matrix, we said, okay, hey, we're going to take A times D minus the quantity of B times C. You can also use the notation that if you just have those bars that are straight bars on either side, rather than kind of like the brackets for the matrix, that will also represent the determinant. So if we wanted the determinant of matrix A here, whether I call it the determinant of A, or I put like the little, almost looking like absolute value signs around it, I'm going to do -1 times 8 minus 4 times a -4. So I get -8 minus -16, which is really like -8 plus 16, and we end up getting +8. Okay, I could do the same idea, and I could ask you for it even if I give you variables. Same idea though. X times 2x minus x squared times 1. So we'd have 2x squared minus x squared. The determinant of this matrix is simply x squared. And as long as x does not equal 0, that would have an inverse. So let's relate. How does it relate back to finding the inverse of a matrix? So remember, if you had a matrix A, B, C, D, then the inverse of that is 1 over the determinant. And then what do we do inside here? We flip-flop A and D, and we change the signs of B and C. Another way to write that is 1 over AD minus BC times still DA negative B negative C. That doesn't change inside there. So why don't you go ahead and practice finding the inverse of this? So let's start by the determinant. We're going to do -21 times -2, and we get 42 minus 3 times 12, 36. Our determinant then is 6. So the inverse of matrix C is 1 over 6. We flip-flop the -2 and the -21. We negate the 3 and the 12. If you want to leave it like that, that is perfectly acceptable. You may also multiply it in, but I am not going to take it to that step. Okay. So as we get to a 3 by 3 matrix, it's a little bit more complicated, and there are 2 different methods we can do. One method is called the diagonal method, and then the other one is the cofactor expansion. So you can kind of choose which one you like. I think there's only one final exam where I've seen like them identify which method they wanted, and they wanted the cofactor expansion method. So if you didn't do that, I would assume they would take off points, but in general, they kind of let you use the method you like. So there's some steps over here on the right, and it says extend the grid by rewriting the first 2 columns of numbers. So we're going to keep the original grid, original 3 by 3 matrix, and we're going to rewrite this first row and the second, and we've extended the grid. Okay, so we're now going to multiply along, in this case it says along the down diagonals. So we're going to multiply these down diagonals. Then the next step it tells you to do is multiply the up diagonals. So then you multiply up. And then it says add the down and subtract the up diagonals. So let's go through, let's see if we can find what these values end up being. So -1 times -4 times -1 is 4. 2 times 1 times 0 is 0. 3 times 0 times 3 is 0. And they're saying we add those. And now let's go through the subtracting ones. 0 times negative 4 times 3 is 0. 3 times 1 is 3. Negative 1 times 0 times 2 is 0. And we would subtract those. So this one became really easy because of how many zeros there were. But we'd end up getting 4 minus 3, and the determinant of this matrix is the number 1. Okay. The cofactor expansion method definitely has a little bit more to it. This is what this is kind of talking about here. It says, hey, we can break down our 3 by 3 matrix into these smaller 2 by 2 matrices that we're going to call minors. And that we can easily find the determinant of a 2 by 2 matrix. The cofactor for any element is the minor or the opposite of the minor, depending on where the element is. So you'll notice it's always going to have this checkerboard pattern. You always start with positive in the upper left, and then it'll go negative, positive, etc. So you can do the cofactor expansion method for any row or column, but you must follow the signs specifically for that. So, to help you see this a little bit better, I've got a little picture up there, but I'm actually going to write this matrix 3 separate times. I'll leave that first one there and call that the first one. And then I will rewrite it twice more. Okay, so the idea behind it is we have to choose one row or column. For simplicity's sake, I'm going to choose this first row, okay? And it's similar to what they did up here in the blue. Okay, when you are doing the cofactor expansion method, now that I have the row chosen, in this case, that I'm going to expand on, this is a positive, a negative, and a positive, following the signs of the top row up there, right? Positive, and then remember the checkerboard pattern, etc., right? So therefore, the first one's going to be positive, negative, positive. And we are going to go along that row. We're going to start with the first, then do the second, and then do the third. Okay. So as we expand along that row, we're going to cross out anything else in the row, and we're going to do positive 1 times the determinant of this leftover 2 by 2. You see that? Negative 4, 1, 3, negative 1. Then we're going to do minus, cross out the rest of that row and column, and then we're going to do the matrix of this 0, 0, 1, negative 1. I forgot to write the coefficient out front, sorry. 2 out front, right, for that one. And then the determinant of 0, 1, 0, negative 1. Plus, cross out everything besides that number, we get 3. And the determinant of 0, negative 4, 0, 3. Okay. So now let's go through and let's find those values. As I find the determinant of this matrix, negative 4 times negative 1 is 4, minus 1 times 3 is 3. So we get 1 times 1. Negative 2, 0 times negative 1 is 0, minus 1 times 0 is 0, so negative 2 times 0, plus 3, and then the determinant here is 0 times 3 is 0, minus 0 times negative 4 is also 0. So plus 3 times 0, so we end up getting 1. Just for kicks, let's say I tried with a different column. So let's say I used, let's try now, actually let me write the matrix first. So let's say you write the matrix, and let's just try this second row for fun. So I still have 1, 2, 3, 0, negative 4, 1, 0, 3, negative 1. Actually, we'll do the first column, why not? Then you can kind of see a column and a row. So if I did the first column, I'm going to expand along this column. So to think about this expansion, you first want to decide the signs. This is positive, negative, positive. So we're going to have positive, negative, positive. We're going to start with 1. Think about crossing out that entire row and column. And what are you left over with? -4, 1, 3, -1. Minus, we now go to the second one, which is 0, times, cross out that row and column. What are you left with? 2, 3, 3, -1. Last one is also 0. Cross out that row and column, and we're left with 2, 3, -4, 1. This one we'd have 1, and then we'd have -4 times -1 is 4, minus 3 times 1 is 3. So we'd have 1 times 1. These are 0, so even if we get a number for the determinant, 0 times anything is still 0, so that's not going to really matter. We still end up with 1. So it doesn't matter which method or which row or column you use, you should get the same. Okay, on this last one, it is up to you. So I'm actually going to leave it to you. I will put, if you want to look at the uploaded notes, I will put the answers on there as far as like the methods that you could use, but you should get a determinant of 83 if you've done things correctly. Okay, so what's the whole point of this? Why do we want to find the determinants? Finding these determinants will actually make it easy for us, if we so desire, to go ahead and solve some statistical equations using it. So it's a rule called Kramer, and I have quite often seen this like on a final, or that also probably means it'll show up on midterm 4, where you're going to have to use Kramer's rule to solve a system of equations. So they give you the system. So if we think about what we use for matrices, we put the coefficients of x and y, and then d and e, and our answers are c and f, right? And you can find the solution by first finding the determinant of the coefficient matrix. So a times e minus b times d. And then we are going to remove the x column and replace with the answers. So we're going to replace this as c and f. So we're going to do c times e for the determinant minus b times f. Same idea here, but we're going to remove the y column and replace with answers. So I'm going to put c and f over here. So a times f minus c times d is the determinant. And the cool thing is, right, is that the x value is going to be the determinant of that matrix dx over the determinant of the original, and y is the determinant of that matrix. We replace the y values, the answers, over the original. So let's see it in action. So let's first find the determinant of our original matrix. So 2, -3, 5, and 1. 2 times 1 is 2, minus 3, -3 times 5 is -15, so we get 17. The determinant of matrix X. So we're going to replace the x's with the answers. So replace 2 and 5 with 4 and -2. Leave the -3 and 1. 4 times 1 is 4, minus -3 times 2 is 6, so we get -2. And then determinant of matrix Y is going to be, leave the x's this time, but replace the y's. So the -3 and 1 with 4 and -2. 2 times -2 is -4, minus 4 times 5 is 20, so we get -24. So now x is equal to dx over the determinant of the original. So we're going to have -2 over 17. And y is equal to the determinant where we place the y's over the original, so -24 over 17. So your answer here is -2 over 17 and -24 over 17. let's go ahead and take a look now at example 7. So once again, I just want you to use Cramer's rule. So we need 3 determinants. The first one is just the original matrix. 3 times 12 is 36, minus 5 times 7 is 35, so we're just dividing by 1. Okay, replace the x's with our answers. (26 times 12, grab out a calculator, and you get 312, minus 39 times 7 is 273. When you subtract those two, you get 39. Same thing here, leave the x's, but change the y's to the answers. So we get 3 times 39 is 117. Minus 5 times 26 is 130. And we end up with negative 13. So technically, x equals dx over d. So 39 over 1, so it's just 39. And y equals dy over d. So negative 13 over 1, so we get negative 13. Okay. Now we are to our 3 by 3 matrices. So we are going to do the same thing. We're going to have 3 determinants. So we're going to find the determinant of our original matrix, which is going to be 1, 1, 1, 2, negative 1, 1, negative 3, 5, 7. And then we are going to have 3 here. So we're going to place the first row with our answers, but leave the second 2 rows. This one, you leave the first and the third row, but you replace the middle row, or the y, with the answers. And then dz, you change the last row. Okay. Up to you how you want to do it. If you like the cofactor expansion, that definitely works. How about I do this? I'm going to do cofactor expansion for the first one, and then I'll do the diagonal for the next one, and then maybe tell you the answer to the other two, let you choose the method you like the best. So if I expand along this first row, I'm going to have a 1, and then think about crossing out that row and column. What matrix are you left with? You're left with negative 1, 1, 5, 7. And then the sign here is now negative 1. Cross out that row and column. We're left with 2, negative 3, 1, 7. And then I'm going to have a positive and then a 1. Cross out that row and column. What matrix are we left with? 2, negative 1, negative 3, 5. So here, we then do the determinant. Negative 1 times 7 is 7, minus 5 is going to be negative 12. Minus 1 times 2 times 7 is 14, minus a negative 3, so it's really like negative 14 plus 3 is going to be negative 14 plus 3, 11. Okay, plus 1. And then I'm going to do 2 times 5 is 10. And plus minus 3 is going to be 7. So you should get negative 12 minus 11 plus 7 should give you negative 16. I feel like I may have made an algebra mistake right here, so give me 1 second. 2 times 7, 1. That's 14. Oh, this is a positive 14 plus 3, so yeah, this is 17. I didn't make an algebra mistake. So this is negative 1 times 17 plus 1 times 7. So this is negative 22. Okay. On this next one, I'm going to rewrite and do the diagonal method and rewrite. Okay, so we're going to go down. So go down your rows, right? And think about multiplying those together. So we'd have 3 times negative 1 times 27 is negative 21. Plus 1 times 7 is 7. 1 times 0 times 5 is 0. And then we subtract the other diagonals that are going down. So on these ones, we're going to subtract these diagonals. Okay, let's do it then. So we get minus 1 times negative 7 times 7 is negative 7. Minus 3 times 1 times 5 is 15. Minus 1 times 0 times 7 is 0. And we end up with negative 22. I'll let you choose which method you want to do for these two, but if you do it correctly, you should get a negative 44 and a 0. So then, to figure out your x, y, and z, x will be negative 22 from your d sub x over your original determinant of negative 22, so it's 1. D sub y is negative 44 over the original, which is negative 22, which is 2. And d sub z is 0 over negative 22, so is 0. So your answer here is 1, 2, and then 0. For this last one, I'll leave it up to you. At this stage, you probably have enough practice, but if you want to go for another one, go for it. This one's not as pretty, but if you decide to do it, you should get x is equal to negative 3 over 81, y is equal to negative 314 over 81, and z is equal to 1 over 81.